Here we are again.
Very good. Looks like we're on.
We are indeed on. Well, Mark, here we are again. Episode 7 of Space Rock's Uplink. How are you doing?
I'm very well. Very good. The weather has finally broken. So I know you've got some, as you just said, biblical weather over there in London, and here in the Netherlands, it's just grey and cloudy. So it's a normal May the 1st.
All right, very good. Well, it's 4 seasons in a day over here at the moment. So if for any reason I disappear, not to worry, I'll be right back. Possibly, we'll see what happens there. So it's a really interesting chat we're just about to have here, Mark. I mean, I am such an admirer of our guest who is coming up, and Katie Mack is an extraordinary communicator when it comes to all things science and so on. But I want to ask a question on behalf of our audience who are already joining us, but also on behalf of myself as well, because I might have been guilty of being confused. What is a cosmologist?
Think of the universe. It starts off at the planet Earth. You've got the solar system, the planets, then you've got stars and the Milky Way, the galaxies. And if you like, beyond that, it's more of the same, more galaxies, more galaxies. But as you look further and further away from us, you're not only looking at other galaxies, you're looking back in time. And so cosmology, if you like, in a very broad sense, is occupied with understanding the way that the universe has changed since its birth 13.8 billion years ago, the way that galaxies have formed, come together, and made stars, made planets like us, but also the larger scale issues. What's the structure of the universe? What's it actually made of in the biggest sense? And Katie's speciality, or one of many, and it's the subject of the book that she's just written, about to be published, is not looking backwards in time, but looking forwards in time. How will the universe evolve from here? And we can make simulations, we can make models of how that's going to proceed. And I'm sure she'll give us some really interesting insights into, what the fate of the universe might be. And that's not the fate of humankind, it's not the fate of the Earth, but on incredibly long timescales, what actually happens in an expanding universe? Where does it go? What's the end game? So cosmology is very much a big picture subject, looking at the overall structure of the universe.
Well, it sounds, to reduce that down, it sounds like it asks the really, really big questions of what this is all about. So it goes everywhere from the granular to the broadest questions, which in many ways they seem almost like existential questions. Just massive ideas about what we're doing and where we are going.
And it's a subject which has changed enormously during my lifetime, during my career, with huge discoveries made by very powerful telescopes on the ground and in space, like the Hubble Space Telescope, which, as we celebrated last week, its 30th anniversary since launch. It's been a huge contributor to our understanding of cosmology. But you're right. It's the kind of question that really does occupy people's minds. Where did this all come from? Where's it all going? Where do we fit in? So it is borderline philosophy in that sense. But at the same time, since my career started, we've actually managed to lose most of the universe through the sort of discovery and better understanding of dark matter and dark energy. And these are key components. They dominate overall what we call the energy balance of the universe. So for all that we know the universe much better now in some details, we actually lost most of it in the last 30 years. So it's slightly embarrassing, and I hope to put Katie on the spot about that.
Well, I think it's a really good moment to actually bring Katie in. She is in the waiting room now, and so we're about to be joined, and we can put it to her immediately. Okay, 1 second. And we are live. Katie, how are you doing?
Good. How are you doing?
Yeah, very well.
Katie.
Thank you
Good to
so
see you
much
again.
for joining us. Yeah, we are receiving. What a pleasure to have you on. And we were actually just we were defining cosmology for a moment there, mainly for my bit. I was actually just hearing something really interesting from Mark. It sounds like in the span of his career and in recent years, we've actually lost track of most of the universe.
In terms of what we actually understand about it. Sure. Yeah. I mean, it's a kind of fascinating yet maybe mildly embarrassing fact that of the things in the universe, we know what 5% of them are made of. So 95% of the universe is dark matter and dark energy, and we really don't know what those are. We have pretty good evidence that they exist as phenomena, as things that affect how the universe acts and how things are forming and all of that. But we don't know what dark matter is. We don't know what dark energy is. We know they're out there, or something is out there doing something, and so we kind of fill in the blanks with these terms, dark matter and dark energy. But yeah, we don't know what they are. We do have a lot more of a handle on dark matter. We know where it is. We know how it moves around the universe. We know what it does to the matter around it. Dark energy is a little bit more mysterious.
So just for the benefit of the audience, because often people get quite confused, they sound the same, dark this, dark that. They're probably completely unrelated phenomena.
They seem to be, yeah. And they act very opposite as well in some ways. So dark energy is whatever we call whatever it is that's making the universe expand faster. So we know that the universe is expanding. Galaxies are getting farther apart from each other. There seems to be sort of more space in between things. Things themselves are not getting bigger, but the spaces in between things are getting bigger. And we know that's been happening since the Big Bang. And for a long time, for the first many billion years, that process was kind of slowing down. It was expanding really rapidly at the beginning, and then slowing over time because all the gravity of all the stuff in the universe is kind of pulling it back together. But about 5 billion years ago, it started speeding up. And that's very counterintuitive because gravity is only supposed to pull things together, not push them apart. And so whatever is making that speed up happen, we call that dark energy. Now, dark matter is an opposite thing, sort of, because dark matter is a kind of matter, so it has gravity, it pulls things together, and it seems to be this stuff that holds galaxies together, that holds clusters of galaxies together, and so we're pretty sure it's a kind of matter, but it's a kind of matter that's invisible to us.
So the one thing there I know confuses a lot of people always, and you mentioned it briefly, but just digging a bit deeper, how can space be expanding, but the things in space, the galaxies, the stars, why aren't they expanding at the same time?
Yeah, so it's about the way that dark energy seems to work is that it kind of gives every little bit of space this sort of tendency to expand, but in each region of space, in a given volume, you don't get more of it over time. You have sort of if you have a volume of space, there's some amount of dark energy in this volume, and it seems like no matter what else is happening, the amount of dark energy in that volume kind of stays the same. So there's this sort of inherent stretchiness to space, but it's not so strong that matter can't come together and form a galaxy, for example. And so if you form a galaxy in that volume, the gravity of the galaxy was able to overcome the expansion of space at some point, and that's going to stay together because there's not going to be more dark energy in that volume to like push it apart. But this is the empty space between that galaxy and a very distant galaxy. There's a whole lot of empty space in between. And as the universe expands, there's more empty space. And then that just creates more expansion because now there's more dark energy, because it appears to be that dark energy is just a property of space. We call it a cosmological constant. And so when there's more space, there's more dark energy. And so when there's empty space, it expands and expands and expands. But when there's matter there, the matter, the sort of gravity of the matter wins.
Right. So if we want to create the classic model is the rubber sheet, and we stretch it out and we put galaxies as dots on it, but they have to be pennies. They have to be actually something solid that they don't get any bigger as we stretch out.
Right, exactly. And another analogy people use is like a raisin loaf or something, and it's small, and then you put it in the oven, and the raisins get farther apart from each other, but the raisins don't get bigger. That's kind of the way that galaxies are moving around in the universe. That, I mean, they're not really moving; it's the space in between them that's getting bigger.
Yeah. So, I mean, if you'll forgive me for saying, it sounds like the further you go, the weirder it gets. I mean, which is kind of counterintuitive, because you would assume that, the more that we study these things, the more rational or the more understandable they become. But it sounds like it's more a process of unraveling than anything else.
Well, our horizons are expanding in some ways. Like, we've had a lot of time to understand how everything works in, the kind of reference frame we live in on the surface of a planet. And as we discover, as our vision expands and we're able to see farther away and see more extreme phenomena, we find the places where our simplified models that work on Earth don't work out there. So gravity is a good example. Newtonian gravity, the kind of gravity that governs, a ball rolling down a hill or a block sliding down a plane or whatever, the kinds of things you do in high school, that works really well for most situations, but it stops working well when that ball is moving at a fraction of the speed of light, or if the gravity of the thing that you're dealing with is extremely strong, like near a black hole. And so we've had to revise our theories of gravity to work with those extreme conditions. And so now we have general relativity, which is Einstein's theory that is based on the idea that gravity isn't just a force between objects so much as it's a bending of the space in between those objects that makes things come together in that curved space. And so, now that we've been able to do these observations out in the universe, and we've seen situations where those effects become really important, where you can't just approximate everything as balls rolling down hills, we've had to come up with something different. And as we continue, studying like the extreme conditions of the Big Bang and properties of black holes, hopefully we'll find new theories that can encompass all of those conditions as well. So, it's always this continuous process of take the theory that works for the data you have and push it out to the extremes, try and find the places where the theory is going to break, and then you find a new theory that encompasses the new observations.
I think that's a really important point, right? I mean, we're hearing constantly in the news these days about follow the science. The science will guide us, not in cosmology necessarily, but in other fields. And yet, scientists love to break science. It's what we do, right? We're constantly looking for ways to make it not true, because that's where the understanding lies. Maybe not in this particular case on planet Earth today, but people often have this idea that science is a rigid thing. It's in textbooks. Well, sure, up to a point. But the job of people like, you and the others in the science community is actually to find the places it doesn't work in some ways.
Well, I mean, that's where we know how to make progress, right? Like if our theory works for every observation we've ever done and in every situation we can imagine, then we don't have a place to go next in our development of understanding. It's only when things break that we are able to make that next step. And it doesn't mean that, you throw it all out. We still do use Newtonian mechanics to calculate things like how aircraft move, or, cars, or even planetary motions, unless you get too close to the sun. But at some point, we needed to go beyond that. And so we have this other version we use for more extreme conditions. But there's an interesting situation in astronomy and physics today, which is that we have a couple of really good models of how particle physics works and how the universe works that are frustratingly refusing to break. So we have some clues that they can't be fully right. So we have the standard model of particle physics, which is this theory of how particles interact with each other, or how the forces of nature work. And that model works really well for every observation we've ever made in a particle collider or other particle physics experiment. But we know it can't be fully true because it doesn't work with gravity. You try and incorporate gravity into the same kind of model, it doesn't fit. And nothing in the standard model of particle physics really works to explain dark matter or dark energy. And so we're pretty sure there's something missing, but we don't know where to go next because it keeps working in the experiments. And so we're trying to find the place where the experiment shows us a clue to where to go next. And it's the same with cosmology. We have this idea of, the universe started with a Big Bang. There was probably this very rapid expansion period at the beginning called inflation, although we don't know for sure that happened. And then, we have a universe full of dark matter, dark energy, and regular matter and radiation. That seems to fit all the data really well. But, we don't have a fundamental understanding of the very beginning, this inflationary period, if it really happened. We don't know what dark matter and dark energy are. The Einstein's theory of gravity, of general relativity, has worked in every place we've tested it, but we're pretty sure that something needs to change with that to fit with quantum mechanics and the particles. So it's this really frustrating situation where it's working too well, and we know it has to be fooling us somehow, but we don't know how. And so we don't know what the trick is. It's like watching a magic trick, and that they're fooling you, but you don't know how. And that's what the universe is doing to us right now.
Yeah, it's phenomenal. I'm sorry, go ahead, Mark.
No, I was just going to pick up on what you just said. There was this beautiful tour de force experiment that the latest set of results were published from these experiments monitoring the motion of stars around the black hole in the center of the Milky Way, and seeing how that black hole is warping space-time as it rotates and causing the motion of the orbit, the orbital position to precess. And it's huge. Mammoth amount of work done over decades, and yet somehow slightly disappointing that the answer is Einstein is right again, right?
Yeah, and it was the same with the picture of the black hole, the Event Horizon Telescope picture. That seems to fit general relativity perfectly well. The same with all the gravitational wave results from LIGO. We see the way that space-time is like disturbed by the collision of black holes, this most extreme thing you can think of. And so far it seems to fit general relativity just fine. There are a few places where people are looking at the data and maybe there's a little bit there, we don't know for sure if there's a problem or not. The data is just not clear enough, but there's nothing to say that general relativity isn't describing the whole picture perfectly well. And that's frustrating too.
Well, I wanted to ask though, because of course, usually when I'm reading about this, it's just, what happened in literally the earliest iterations of the universe, just after the Big Bang. What was all that? But you've written a book that concerns the other end of the scale. So
yes.
Tell us about literally, I think one of the best titles I've read in a really long time. Come on, the end of everything. It sounds.
Yeah. I have a copy of it. Hold on.
Okay.
This is one of the early copies, so it doesn't come out until August. It's the publication date is August 4th, but it's called The End of Everything, Astrophysically Speaking, and we had to put the Astrophysically Speaking on there to make sure that people knew that we were talking about, the universe. Really meant everything literally. And yeah, it's about the end of the universe. It's about how that might happen, what it would look like if we could see it happening, if we were there. And it's a fun topic because, yeah, as you say, there's a lot written about the very beginning, about where we came from and all that. But you don't read as much about where it's all going, how it's all going to end. And so I thought it would be fun to take a few different scenarios and explore them and talk about how we're trying to figure this out. Like, is this even a scientific endeavor to think about the end of the universe? And is the universe going to end? And it really looks like it is. So, we might as well figure out what that's going to be like.
Well, it's interesting that you say that because there's so much to explore and unpack from that. Just before we had you on, I was asking Mark, what is cosmology? And he said something really interesting, which was that, in some sense, perhaps it almost shares a border territory with philosophy. You're saying, is it even a science thing? And I just wondered what your thoughts were on that.
Yeah, when I first, one of the ways that people often encounter the word cosmology is in the context of religion. So a particular faith might have a cosmology, and that's a vision of how the universe is put together in that faith, with whatever deity there is, how things work, when you die, and where the world came from and where it's going and all of that. And so initially it was this idea of a religious notion or a philosophical notion, and there's still, it's still perfectly valid to talk about cosmology in those realms. But as a scientific endeavor, it's a little bit more recent that we've been able to really study the beginning of the universe and the end of the universe and how it's evolving over time. The discovery of the expansion of the universe was in the sort of 1920s, 1930s, around then, when you started to see that galaxies are moving apart from each other. Before that, we didn't know that the universe was changing over time. And there were there were theories that maybe the universe just stays the same all the time, and, you know, stars might die and so on, but the fundamental structure of the cosmos was stable. And now we know that it had a beginning, that it was very, very, very different 13.8 billion years ago, and it's evolving and it's changing and it's becoming something else. And so now that we can do observations and we can see the evolution of the cosmos over time, we can really unpack that and see it as a scientific endeavor. I think that's one of the coolest things about cosmology is we really can see it. We really can see the past, the history of the cosmos by just using the fact that light takes time to travel. And so when we look at something, we're seeing as it was when the light left that thing. And so when we look at a really distant galaxy, we're looking at it in living in a universe that was much younger than our universe is around us now. And so we can see how the cosmos has been changing by looking directly at the time when it was different. And we can do that all the way to the Big Bang. We can see the afterglow, the leftover light from the Big Bang, from when the universe was hot and dense and glowing with heat. We can see that glow if we look far enough away with microwave telescopes. It's very, very cool.
It's very cool, and also very mind-bending as well.
Yeah.
Because you're basically talking about not looking at distances, but looking at times as well, which is, I mean,
Yeah.
I guess we're talking about raisin loaves and all these things. I mean, immediately our language begins to fall down in trying to describe these things, because we search for metaphors that are familiar to us, but there's really almost no way to describe what you're doing. You just have to just try and imagine it, I suppose. From my perspective, it does make my head spin a little bit.
Yeah, definitely. You know, the concept of time, the concept of what it means to say something is happening now gets really complicated in astrophysics, because, you know, if we see a supernova go off in the sky, you know, we see a star explode, we say, oh, that just happened now. Actually, it probably happened, you know, maybe millions of years ago, and the light's just reached us now, depending on how far away the supernova is. And so, you know, okay, it happened millions of years ago, but we're only getting the information about it now. It couldn't have affected us before now. So do we call it now? Do we call it then? There's this whole concept of causality where, you know, the time light takes to travel from one point to another tells you whether or not those things can affect each other. And so there's some sense in which there's a star exploding right now that we're not going to know about for a million years. And can we talk about that as happening now? Or does the fact that it can't possibly affect us until a million years from now mean that we should talk about it as a future thing? You know, so you have to think in this weird fourth dimensional way about space and time tied up together in envisioning this sort of larger cosmos, and it does kind of mess with your head a lot.
And yet, weirdly, of course, when it comes to looking back in time, 10 billion years, we do talk about the past. So, you know, we kind of get over it. When it's near to us, we talk about it as being now. But when it's a certain distance, we actually say, well, actually, you know, it's a different universe. And funnily enough, I don't know if you ever noticed, but if you listen to historians talk, they talk in the present tense an awful lot. You know, they say things like, and now the king goes to get to unlock a prisoner. It's like, what do you mean? It happened hundreds of years ago. So I think they live in a different time warp as well as astronomers. But to flip things around though, so, you know, we talk about this 13.8 billion years, which of course is ludicrously unimaginable. And there's all sorts of metaphors for, you know, how tiny a fraction of the total lifespan of the universe we've occupied. But that's nothing compared to the timescales on which the universe is going to die, right? So in some broad sense, we're right at the beginning. And there's a lot of stuff to go on. So give us a bit, you know, pick whichever one you want, right? I mean, closed universe, open universe, flat universe. What is going to happen?
Well, so the most likely thing based on the data we have now is something called the heat death. So this is where the universe is currently expanding. It continues to expand, and it continues to speed up in its expansion due to dark energy, this cosmological constant, assuming that's what the dark energy is. And if that's the case, then the way that it'll work is that, you know, galaxies will continue to just get farther and farther apart from each other. You know, each sort of cluster of galaxies or group of galaxies that's already gravitationally bound will stay bound, and some of those will merge. You know, we're going to merge with the Andromeda galaxy next door in about 4 billion years, but our little group of galaxies is going to get farther and farther apart from other more distant galaxies. And so over time, each galaxy or group of galaxies gets more and more isolated because there's so much more space in between. And it's one of these things where, because the universe is expanding and everything in the universe is kind of diluting as the volume of space gets bigger, you know, there's the fraction of the universe that's made up of matter is going to go down and down and down, because the dark energy you just keep getting more cosmological constant as you have more space. And that's a weird concept too, but it means that over time, that really dominates the expansion of the universe, the dynamics of the universe. And so you end up with a universe that just gets more and more empty as everything gets diluted out. And so each region of the universe, each galaxy is going to kind of be alone in its little pool of light. And it'll be, at some point, we'll stop being able to see other distant galaxies. So in around maybe 100 billion years, it'll be impossible to view galaxies outside of our local group, because they'll be so far away, they'll be moving away from us so quickly with the expansion of the universe that the light won't be able to get to us in any way that we can see. And so we're going to lose the ability to study the larger universe. We'll lose evidence for the Big Bang at some point, because these things will get so far away. And that's 100 billion years, you know, so we've only had 13.8 billion years. That's 100 billion years, and that's just the beginning of the really end, right? Because once you're isolated, then you don't have any more galaxy collisions to bring new gas in to make new stars. And so the stars we have will start to burn out, and you won't get new ones. And so you'll have a whole lot of dead stars, a bunch of black holes, and then the black holes will start to evaporate away through this quantum mechanical process called Hawking radiation. And particles will start to decay. And eventually you end up in this very, very cold, dead, empty universe. And once you get to the final stage of that, that's called the heat death. And in terms of a number for how long that takes, like it's hard to even describe, because it's so many orders of magnitude beyond anything that makes sense to us. But what it means is that, you know, we're in the interesting part of the universe right now, the interesting part of history. And then at some point, it's just going to be cold and dead and empty forever, basically. And there's going to be nothing left, which is a really kind of sad story. But that seems to be where we're headed. Now, there are other possibilities, and in my book, I talk about some of those where, you know, maybe the dark energy isn't a cosmological constant. Maybe it's something else, and it could change over time in a way that would either turn around and make the universe collapse, or start ripping galaxies apart because it gets more powerful. There are also possibilities where the universe can go through cycles of Big Bang and Big Crunch. And there are situations where you can have sort of universes smacking into each other to create new Big Bangs, stuff like that. And my favorite one is one called vacuum decay, where you can have a kind of quantum event happen in one point in the universe and create this bubble that of a different kind of space that expands through and destroys everything. And that one could technically happen a lot sooner, but it probably won't.
Maybe right now, who knows?
Yeah, maybe.
To clarify, when you say sooner, do I need to worry?
You don't need to worry. There are a few reasons you don't need to worry. One of them is that it's not likely to happen soon. So if vacuum decay can happen, then the likely time we'd have to wait for it to happen in our sort of observable universe is something like 10 to the 100 years, maybe more. So it's not likely to happen anytime soon, but it's based on a quantum tunneling event, which means that it's just a kind of quantum transition. It's a probability-based thing. You can't say for sure when a quantum tunneling event is going to happen, just that there's some probability it'll happen at some point. And so if vacuum decay can happen, then it could technically happen at any moment, at any point in space. It's just very, very unlikely. And you shouldn't worry about it for a number of reasons, even beyond that. One is that you wouldn't feel it. You wouldn't see it coming. You wouldn't feel it. The bubble expands at about the speed of light, so you don't see it coming. It doesn't hurt, and like nobody's left to miss you or anything. It's not sad. You kind of don't notice. But also, the whole idea of vacuum decay comes from taking the standard model of particle physics, which I said, passes every experimental test, but we know it's not complete. It's taking that theory and sort of extrapolating it beyond the realm where we think it's probably, reliable. So it's very possible that something else, the next theory we come up with of particle physics, will say that vacuum decay can't happen. But we don't really know for sure. So that's one of the more fun ideas that I got to explore in writing this book, is this idea that we could just kind of blink out of existence.
But I wondered if I could ask you a bit about your writerly process as well, of course, because I mean, to condense concepts that are utterly vast, right? Beyond the constraints of language in many cases and all that. I mean, you seem to do this effortlessly, but it must be difficult to sort of stay true to the findings, to what the theories are, what the state of play is. And you'll be able to reduce it down to kind of make it consumable to people like me.
It's, for me, I've had a lot of practice in talking about science for non-science audiences. And so as you do that, as you do a lot of talks and write a lot of articles, and even on Twitter, I talk about astronomy and physics a lot on Twitter, you get a lot of feedback. You find out what kinds of ideas are confusing to people and what people can really get. And so that, I've been doing that for so many years. I sort of get a feel for, this idea is going to be confusing. This is a thing that I need to really spell out. This is counterintuitive. And that's helped me to not get so caught up in, what I've learned over my education as to forget that I didn't always know that. And so that's definitely helped. But it is a tough balancing act, because you want to give the best version of the science. You want to be really true to the facts. You don't want to be misleading. You don't want to be sloppy with your words. But you also don't want to just be so, precise that people just have no idea what you're talking about. And if you're writing for a popular audience, you also want it to be, fun and interesting, not so dry with the details that people don't even want to know what you're talking about. And so the thing that I try and keep in mind all the time is, if I'm going to use an analogy or, some kind of metaphor for a process that I'm talking about, I want to make sure that I make it clear what the boundaries of that metaphor are. So where it breaks down, where I'm making an approximation, where, you shouldn't take what I'm saying completely literally, but it'll give you a feel for it. And I try and be really aware of places where it's more complicated than I can explain, and I will tell you it's more complicated than I can explain, but I'll also say, but here's something you can get out of it anyway. And so in the book, I do a lot of that. I get into some ideas of particle physics about how the forces of nature change at different energies and things like that. And I say, this is complicated. This is heavy mathematical theory, but here's an analogy. This is the kind of way we can think about it. Here's a little bit about what we mean. And, if you're really keen, then quantum field theory is a fun thing to learn. But, in the meantime, let's give you an idea about it.
So let me go back to the question of the eschatology, the end of the universe. Everybody, there's this constant hoo-ha in that, we need to get off the planet Earth in order to survive, because the sun's going to go red giant in 5 billion years. I mean, look, we're 200,000 years old as a species. We're not going to be around. But in a broader sense, intelligence as an information processing thing has a problem as the universe gets older, right? So let's not go in. Well, let's go into the hardcore and talk about entropy for a moment, right?
Okay, yeah.
How does intelligence, or how does information processing work later in the universe? Because it relies on there being less entropy today than there will be in the future. So is there a role for intelligence deep in the far end of the universe?
Well, so this is a really interesting topic that people have thought about in cosmology for a long time, whether or not it's possible to continue some kind of life, some kind of intelligence indefinitely. And in the 1960s or 70s, Freeman Dyson, who's famous for the Dyson sphere, who unfortunately just passed away recently, he wrote a paper about how in a particular kind of expanding universe, if an intelligence creates machines that are constantly slowing their processing and hibernating and doing this, then they can do an infinite number of calculations over the course of, an infinitely old but constantly expanding universe. Unfortunately, if the universe is accelerating, that changes the picture in such a way that doesn't work anymore. And you really do succumb to entropy and disorder in the end. And part of that has to do with the fact that a universe that's dominated by dark energy has what it's called a de Sitter horizon. It's a sort of, it's kind of like having a horizon like a black hole, but you're inside it, but the space is a different shape. In any case, it means that there's a kind of radiation that comes from all directions that results in, you end up in this maximum entropy state. You have sort of maximum disorder in the universe. And so once you get to this maximum entropy state, the fact that the second law of thermodynamics tells you entropy can only increase over time means that nothing can really happen anymore in any meaningful way, because if you define the direction of time by the direction where entropy is increasing, where disorder is increasing, then at some point you can't increase disorder anymore. And therefore you can't do anything. Anything that's done, any process increases entropy. If you have a pendulum going back and forth, you're going to lose a little bit of that energy to friction in the bearings of the pendulum, and that friction creates a little bit of heat, and that increases the entropy of the universe a little bit. And so you can't have that process happening in a situation where the entropy is already maxed out.
Right.
And so you can have little fluctuations. You can have like a little statistical fluctuation of, something can kind of appear for a minute and then degrade again.
Right? That's us, we're entropy decreasing for 70 years, and then we go back to being increase of entropy.
Well, I mean, we're increasing the entropy around us by existing.
No, exactly.
But yeah, so you can have a little pocket where the entropy there goes down for a little bit and then it fluctuates back up. But you can't have, construction. You can't have order coming out of that state. And so when you get to that state, you're done. And time doesn't mean anything anymore either, because you have no arrow of time anymore. So that also is really weird. You end up in this sort of eternal state of timelessness, kind of like the time is there, but the direction of it isn't. What does that even mean? So I get into that in the book a little bit. It's really a trippy idea.
So the arrow of time, right?
Yes.
So time obviously only moves in one direction, but apparently it doesn't. I mean, it
moves in one direction. It moves in the direction of increasing entropy. It's just that when you max out entropy, it doesn't have anywhere to go. So you don't have a direction anymore, right?
Yeah.
So a weird thing about physics is that in most of what we understand about physics, the direction of time, the arrow of time, isn't really part of the picture. The only way it really shows up is in the increase of entropy over time. Most of the processes of physics are basically reversible one way or another. And so it's entropy that really defines the fact that time has a direction at all. But if entropy doesn't give you any help anymore in figuring that out, then time becomes meaningless.
Okay, so we're in the world of science fiction, except it's not.
Okay, yeah.
Can you, I mean, thinking about these things and working on these things as a living, can you actually enjoy science fiction? I mean, sometimes, what we actually do seems weirder than science fiction, right?
Oh yeah, but I love science fiction. I mean, I don't require my science fiction to be fully scientifically accurate in every possible way. I do appreciate it when it's, internally consistent. And that I appreciate that for all of my fiction. If I'm reading a book about, a fantasy book about elves and fairies and things, I appreciate that being internally consistent too. Elves can only do this one thing, fairies can only do this other thing, whatever, right? Don't have them switching around. And it's the same with science fiction. If there's some, tweak to the laws of physics, I want to know that always works in the same way, and that it doesn't, it doesn't break some other part of the story. Sorry, there's a there's a cat meowing in my house right now. So if you hear a meow,
you do.
If you hear a meow, that's my foster cat Mochi.
A very recent, pretty Siamese cat, or is it Burmese?
Yes, she's. So I think she's a part. She's like a Siamese cross, but she's very loud sometimes. So
that they are, yeah.
But anyway, so yeah, so I love science fiction. I love the way that sometimes you can take an idea and go in a direction that you couldn't possibly go within the confines of our physical reality, you know, and how it allows us to explore aspects of human nature. You know, when you read about, you know, living in space for thousands of years, or you know, how weird new technologies or massively extended lifespans or you know, communication through chips in your brain, whatever, all of those things are really fascinating to read about and to watch as media, to see how humans would respond to that, and what it would do to our lives. And sometimes it's just escapism, you know. I love to read books about spaceships, you know, just like I like the idea of going to space and hanging out in space and seeing different planets and all of that. And so, you know, I consume a lot of that kind of media as well.
So I love to ask this of people because, you know, you ask 5 different people, you get 5 different stories. What first sparked your imagination, both in the worlds of science and indeed science fiction?
I mean, I've always been interested in science fiction, so that's definitely, you know, I used to read the Analog and Asimov magazines when I was a kid. My mom had a subscription, and I would steal those from her when she was done reading them. So I've definitely always loved, you know, Star Trek and Star Wars and all of those kinds of things. But I think my interest in physics and astronomy really comes from just a curiosity about how things work, you know, how everything fits together. I was the sort of kid who would take things apart, you know, like I'd unscrew the remote control for the TV and see what the circuits were and figure out how the little toy cars work and all of those kinds of things. And so I think that idea of just wanting to understand how things work, that's what really brought me into physics and astronomy. And, you know, a lot of astronomers get into astronomy through stargazing and things like that. And I grew up in Los Angeles, where the night sky is not particularly exciting. There are stars, but not that kind. And so the idea of just, you know, looking into this beautiful expanse was not so much an option, unless I was going out into the mountains or something like that. And so for me, I really got into it through physics, through trying to understand everything. And then when I was sort of 10 years old or something, I think I picked up A Brief History of Time and started to read about black holes and the Big Bang and time travel and all these kinds of things. And I just thought that was fascinating, and I wanted to learn all of the kind of mind-bendy stuff.
Well, mind-bendy stuff is good. Sorry, go ahead, Mark.
Yeah.
So we were just talking about it before we came on air about we don't think it was the first time that we met, but the second time we met was also in Australia, but when we went on a mini tour with Buzz Aldrin, which is, you know, slightly bizarre thing to do, right? You know, go out on stage with one of the first people on the moon. But here we are. Yeah. It's, you know, just yesterday there was a big announcement about new possible ways of going to the moon, new technologies in the next few years, maybe. Well, let's see. But yeah. But you know, an area which I know preoccupies you, or at least, you know, you're vocal on it, and I think, you know, very appropriately so, is kind of changing the model of how we've done things in the past, you know, partly politically, partly in exploration, partly in space, you know, and there's a lot of kind of gung-ho about putting, you know, footprints and flags back out there again. And in Europe, we're part of this program. We're engaged, we're involved in the lunar exploration stuff and going to Mars. But, you know, from your insight over the last few years, is it possible to change the way that we do space exploration in the very broadest sense, in a cultural way, that we do it better?
I think that we can. I think that it's a difficult thing because we have to deal with a lot of baggage around this idea that space exploration is like this race between nations to kind of, you know, have this big macho thing and be the first to do something. And right now we're in an interesting time because private exploration is becoming more important for the space industry, and you know, however people decide to do that, it's not up to as many people as if it's a national organization or an international cooperation. If somebody decides I'm going to send a rocket to the moon or to Mars on my own dime, it's hard to have any say in that if you're not part of that organization. And so I do think that we have an opportunity to think about how we talk about space exploration, what we prioritize in space exploration, make sure we try and use international cooperation a lot more, and not make it a competition. We have this possibility of really having this be a thing that we come together to do as a species. But working out the politics of that, the finances of that is complicated. And I think that something that can help is for us as a sort of space community to reiterate how important those aspects are, how important, inclusion and cooperation are, and to make sure that when we talk about things like going to Mars, we don't use a lot of sort of very loaded language about colonization and this kind of manifest destiny kind of ideas that people throw around when they talk about things like Mars. And so I do think that the way we talk about these things, the way we promote these things, we can use to really change the direction of the conversation potentially, and hopefully make sure that we do it better as we keep going. The National Geographic series Mars, the TV series, did a really good job of going through a lot of the issues there about things like the use of resources and sort of environmentalism. If you move to another planet, what responsibilities do you have to preserve that and to work together and to make sure that people and resources aren't being exploited? So I would definitely recommend that series if you're interested in a cool science fiction story, but also a lot of really interesting discussion about all of these topics. But yeah, it's an ongoing conversation. It gets really heated sometimes when people have different opinions about what we should prioritize in space exploration, but I think it's a conversation we need to have.
Indeed. Well, I mean, not to be solely self-referential, but part of the inspiration for space rocks was really just it came from just this really overwhelming sense that we live in an incredibly exciting and pivotal moment, when it comes not just to space exploration, but also, our involvement in space and all these things. And I guess what's so important, is the clarity and transparency of communication. Now, what you've done so effectively, Katie, is to bridge the gap. I mean, you haven't just gone into academia, you've also come out of it again. And I mean, how important have things like social media been to getting these ideas out there and sparking debate and dialogue for you?
Oh, I mean, I think, I learn a huge amount on social media, just listening to people from different communities talk about what's important to them and seeing these debates happen in real time among people who have a different perspective or a different background. I found social media to be just a huge learning opportunity for all of that, and a way for me to try and share my ideas as well, and to be part of that conversation. But Twitter can be a difficult place, but I do think that it's a great opportunity to really have conversations that can change how you think about the world and how you think about other people's perspectives. And for me, that's been invaluable. And I'm really glad that I have that opportunity and to just, talk to more people about the things that I find really exciting and the things that I find important. Lately I'm talking a lot about politics and public health and things like that, because that's what's going on around me, and that's what I find important right now. So I think it's useful to have those conversations too. But even if we're just talking about science and space, there's so much of an opportunity to have more connection with just a much broader group of people, and not just be talking to each other within academia, because I don't think that's all that helpful, as if we want to be responsible and engaged with the world as academics and not just be talking to each other. We need to listen as well and see what other people are saying.
Indeed.
I can only echo that completely. I mean, I came to it very late, and to some extent, I came to it because I had a bunch of people I was working with who were using social media to communicate what we were doing in our missions. And I would keep saying, well, why did you do that? And why did you do that? You know, and say, well, if you actually were on social media, you understand why just some of the tricks, as well as some of the way of holding a dialogue. And yet, as you know, as well as I do, right, there are still so many people that just view it as a total waste of time. It's just idle gossip. It's just chit chat. And I vehemently disagree with that. I mean, of course, it can be that if you choose for it to be that. Sure. But that's like anything you do in life. You can abuse or use it. And certainly it's changed me. I mean, I know that sounds a bit trite and a bit, fake profound, but I think about things quite differently now. Because of the conversations, I mean, I'm not going to name names, but just yesterday I managed to get into a fight with a debate with a senior broadcaster in the UK over whether talking about an asteroid coming close to the Earth was dodging a bullet when it was actually 16 times further away than the moon. And he's a broadcaster I respect, and I would watch him every day, but kind of there was no room for correction. There was no room for saying, that maybe that's slightly dangerous, that use of language, because just the day before somebody had come to me and said, can you talk to this lady? She has an autistic son who's incredibly scared because he's read this asteroid's going to hit the Earth. Right. And I thought, it's just sad that we're in that position, particularly on top of coronavirus. And then to have it kind of dismissed as, oh, well, who cares anyway? It's just, it's not, so I've learned an awful lot by being on there. And you're active as well, Alex. I mean, I think I actually have the least number of followers of any of the three of us. So, it's certainly changed the way I think about the world.
Yeah. Yeah. And I think that idea, that point that, the way you talk about things, when you have a big platform, like somebody who's broadcasting for a major organization, you have a responsibility to be thoughtful about how you talk about things and what effects those might have. And that's something that I've definitely thought an awful lot about as my platform has grown on Twitter, is, the responsibility to really take into account how my words will be received, not just what I mean by them, or how many likes and retweets I might get from saying something in a particular shocking way or whatever.
But just to flip that around, because I know it's something that, again, because of the matter of scale, is, on the other hand, it's got that weird distorting effect that everybody thinks that you're their friend, or that they can depend on you for something as well. And when the kind of stratospheric numbers that you and Emily Lakdawala, Phil Plait, and so on have, that must place a burden on you as well, and how you insulate yourself from that kind of expectation that people put upon you. How do you deal with that, actually? I mean, how do you just have to cut yourself off sometimes?
Yeah, sometimes, it's I do have to step back sometimes, and I have to think about, think about how people see me, and to try to be understanding of how people might have a kind of distorted picture. I've been pretty lucky. There've only been a few occasions where I've gotten like a huge amount of trouble from the internet. But I do have to keep in mind things like, some people might have weird intentions when they talk to me, and I have to be a little careful about the personal information I put out there and stuff like that. And I have to protect my privacy and my safety in ways that I wouldn't have to if were not known. And that's been a challenge at sometimes. But I also, I get a lot out of being online and having a big platform. And for the most part, people are very nice. It's only occasionally, if something I say blows up in the wrong communities, or if somebody gets a little bit too enthusiastic, then things can be difficult. But I've been pretty lucky, and it's been a long time since I've had to deal with a really big problem. So it's been mostly pretty good lately. I mean, who knows? Maybe tomorrow something I say will kick off some kind of firestorm, but for the moment, it's not too bad.
Cool.
Well, that's good to hear. Well, speaking of enthusiasm, people have been very politely enthusiastic watching our stream now, and I just wanted to maybe bring them into the conversation. We have people watching from all over the place, really. Canada, Chile, Belgium, the Netherlands, and the list goes on. And they have some really terrific questions.
Okay.
And I think one is really pertinent to what we were just talking about a few moments ago. This one comes from Alan Dowson. He says, listening to you talk, why do you think there aren't more scientists in politics?
In politics? I mean, I think that a lot of what we're trained to do as scientists is to kind of work quietly and talk amongst ourselves, but we're not really trained to get involved in the wider world in the way that, you know, maybe a lawyer or a I don't know, a business person or somebody is encouraged to do. And I think that there are some scientists in politics, and some of them are doing great things. And I think that as more scientists are encouraged to communicate and to connect with the wider world, maybe those numbers will go up. But I think that a lot of it is just, you know, the kind of training we have. Unfortunately, a lot of scientists still are just not encouraged to do much of anything outside of their research and their teaching, and so that limits, you know, how much people really get the experience of being out there, and the kind of inclination. You know, a lot of times people see science as being a very solitary endeavor, and there are times when it can be, but I think that notion that we have to kind of like sit alone in a room with a chalkboard. I mean, I'm doing that right now, obviously, but this is a strange time. It's not usually like this. Usually I go to the office every day and I talk to people all day, and I go to seminars and I have coffee, and I you know, exchange ideas, and we bounce things off each other, and it's a very interactive, very social thing, really. But I think the fact that people don't see it that way, don't see it as a creative industry, a lot of times people who would be more inclined to reach out and get involved avoid science for that reason. I think that's a little bit of a shame.
Yeah.
Very fair.
I think there's also, you get to some extent the reflection of the broader culture as well. If you think about China has lots of politicians who are engineers. America, very litigious society, has lots of lawyers who are politicians, and in Britain we have lots of public school boys who are politicians. So, you know, maybe you have to change the whole of society and change politics. Which one comes first? But
well, you know, I guess you know, perhaps without going down the rabbit hole, I mean, I suppose what we're seeing in our situation now, you know, is a battle with unreason. You know, so perhaps you know, the advantage, you know, of science, of course, it creates an intellectual framework for people, and perhaps, speaking for Alan, I don't wish to infer from what he is asking, perhaps that would benefit politics, perhaps if people were better at interpreting the information that's available to them. So we have a wonderful question from Hannah Vinson, and this is kind of playing on my mind as well. Is dark energy going to pull our galaxy apart?
So probably not. If dark energy is a cosmological constant, this which is an idea that Einstein first put together, which is just a sort of property of space that, you know, empty space kind of has a bit of stretchiness in it, then it can't pull a galaxy apart, because once something overcomes that stretching of space and forms a bound object, then that thing stays bound. But if dark energy is something different, something we call phantom dark energy, which is a hypothetical thing that dark energy could be, then instead of, you know, the amount of dark energy in a region of space staying the same all the time as the universe expands, the amount of dark energy would increase in that volume. And so something that formed a bound object in the past would start to be stretched out by the expansion of this phantom dark energy. And if that happened, then yeah, it would rip apart the galaxy, it would rip apart the solar system, it would rip apart the Earth, it would eventually rip apart molecules and atoms and space itself. And that's called the Big Rip. And that's one of the ways that I talk about in my book, where that the universe could end. It's not one of the favored ideas, but it's not something we can rule out with data right now either. So it's kind of a fun possibility.
Wow, that's a big one. We've got a great one from Leo, who asks, are galaxies moving away from us because there's more space being created between us and them, or because they're actually moving away from us relative to space?
That's a great question. It's the former. It's the fact that there's space being, you know, coming into being between us and the other galaxy. Every every galaxy is more or less at rest. I mean, there are galaxies that are orbiting each other because they're in clusters or whatever, but on large scales, you know, clusters of galaxies, groups of galaxies are pretty much staying still, but the space in between them is getting larger. So it's not like we are moving through space and like running into things. Our galaxy is staying put. You know, other galaxies far away are staying put, but the space in between us is growing. And so from our perspective, it looks like they're moving away, but it's as though, you know, we're on, you know, we're standing here and there's somebody standing on a treadmill being pulled away, you know, as the treadmill or the people mover or whatever takes them away. They're not walking anywhere, but they're being farther away because there's more space in between. And so it does look like things are receding. And when we see the light from distant objects, we see that light being stretched out in the similar way that it would be if they were just moving through space. But we think of it more as the light is being stretched out by the expansion of the space in between.
And one of the things that people, of course, struggle with in that regard is the fact that things can actually move faster than the speed of light, in a sense. I mean, it's not, if they were really moving, that would be the limit, but actually they can apparently move faster than the speed of light, further away from us. And that's still scrambles my brain, but that's why I'm a Milky Way astronomer and don't play around with cosmology.
Well, and this is one of the cool concepts is that if things really were moving through space, then there would be some center of that motion. But because everything's basically staying still and the space is getting bigger in between, what's really happening is that everything's getting farther apart from everything else because all the space is getting bigger. And so there is no center of that motion. If we're standing here, we see all the distant galaxies moving away from us. If someone is standing on a distant galaxy, they would see us moving away from them and all the galaxies around them moving away from them. And so if the whole space is getting bigger, everything seems to be moving away from everything else on a large enough scale. And so you get a very different picture of what's happening if you understand it as things are staying still, but the space in between is getting bigger. But that also means that something that's farther away now is moving away from us more quickly, apparently, because there's more space in between us and that thing to be stretching. And so that means that for even if the expansion were very, very slow, you would still get to a point where you're far enough away faster than the speed of light as a recession speed. So it's this very cool, weird thing that comes about because space is expanding in the same way in every direction, everywhere.
Cool and weird are definitely ways I would describe it. Emphasis on weird, but that makes it cool, right? So indeed, it's a kind of weird. So Sean from Alberta asks, I think, a great question because I'm kind of curious about what a day in the life looks like. He says, what kind of evidence are most important for your research?
What kind of, sorry, what's most important?
What kinds of evidence are most important for your research?
So the work that I do is in theoretical cosmology. So I don't do anything with data. So I don't use telescopes. I don't do experiments. I don't process images or data coming from telescopes or experiments. So what I work with is mostly, observations and experimental results that other people have done. And I try to put those in the context of the theories that are out there and figure out how the theories that people are coming up with, people are testing, can connect with the data that we have from actual observations and experiments. And so I'm trying to find kind of new ways to connect theories about the universe, about particle physics or cosmology with data that we already have or that we'll have in the future. So the kinds of things that are kind of most interesting and useful to me are observations or experiments that are kind of pushing the edges of what we know. So, for example, I'm interested in radio astronomy that's going to be looking at the gas from which the first galaxies and stars formed. So this is something called 21 centimeter radio astronomy. We're going to be able to use that in the next few years to really see how the first stars and galaxies really starting to get going. And so because that's this whole new data set that's going to come, we're going to get new insights about the cosmos. It's important to figure out, okay, if we see a certain thing in that observation, what does that tell us about our understanding of things like dark matter, or how the first stars worked, and things like that. And so I look a lot at the kind of observations and experiments that are really pushing the edges. But I also think a lot about ways that we can use observations we can already do, or observations that are coming up, to test things in a new creative way. So for example, when I was a postdoc working in England, I was thinking about how we can use some of these new radio telescope arrays to look at the possibility of cosmic strings, which are these kind of strings and loops of energy that are hypothesized to maybe exist out there in space. We don't know, we don't have any evidence that they exist, but if they did, then there are a number of things they would do. And one of them would be that they would cause interesting effects in the images from these radio telescopes. And so that way of connecting an observation to a theory in a new creative way, that's a lot of what I try and do. And it's really fun, because you do get to be creative. You do get to, I talk to the theorists, I find out what the cool new theories are. I talk to the observers and experimentalists, and I find out what they can actually do and what kind of data they're going to get. And then I try and make new connections between those things that haven't been considered before, or that's use the telescope in a way nobody intended to use the telescope, but it's going to give us this data that we can then use to learn something about fundamental physics.
Okay, very good.
Yeah, I was just going to say, you've just illustrated it extremely well, that the interplay between observations and theory pushing each other both ways. Of course, it can snap occasionally. I'm, again, not naming any names. There was one famous theoretician in my field who was famous 20 years ago for turning up at talks, and observers would go up and show their data on the screen, and he, and of course it had to be a he, would stand up and say, "Sorry, your observations are wrong. They don't agree with my theory." And completely straight-faced. It got a little bit boring at some points, but yeah. But no, but this feedback, we don't necessarily know what to build unless we've got something to be shooting for, right? I mean, just building a big thing sounds like you're going to collect more photons, but yeah, fine. But maybe you need to build it in this piece of wavelength domain, or time domain, or spatial coverage. And I think astronomy has become much more driven by the interplay between theory and observation in my time, rather than just go to a telescope, take a picture, and then explain what you see. So we're building missions like Euclid, which and WFIRST missions to look at dark matter and dark energy. And of course, there's some very specific parameters we want to measure. They're not just going out there to take pretty pictures of space. In fact, the pictures may not even be very pretty, because they're not designed to be, but they are super finely tuned to deliberately get in and provide the numbers which you guys need to then see, does this fit or does that fit to that model of dark matter and dark energy?
Yeah, and especially with space missions, it's so important to put together a science case and justify every dollar you're going to spend, because otherwise nobody will fund you to put this thing out in space. And so you really have to know, you have to say with very clear predictions what this thing is going to see, what it's going to tell us about the universe, what we'll learn that we didn't know before, how it fits with other observations. And then once that is planned, once you know what the parameters of the observation are going to be, then there's room to say, okay, well, maybe we'll see this unexpected thing, or here's how, by looking at all these galaxies, we can learn something about dark energy that we didn't know before. All of those kinds of things you can tweak after the fact, but you really have to have a good idea of where you're pretty sure you're going to go, and then hopefully you see a bunch of unexpected things and you learn something cool as well, that in addition to whatever you're trying for.
Very good. Okay, so a couple more questions, and we have some great ones. One is, well, it might as well come from me as well. Sophia in Canada asks, do you believe in a multiverse?
Ooh, so that's a good question. It depends on what you mean by multiverse. So there are a lot of different ideas of a multiverse out there, and they come from different kind of tweaks to our understanding of physics. I think one of the ones that is most prevalent in things like science fiction is what's called the many worlds interpretation of quantum mechanics. And this is the idea where every time a quantum mechanical event happens, like every time you measure the position of a particle to be here and not over there, that's a kind of choice between two possibilities. that has no basis other than probability. You know, you had a 50% chance of measuring it here, you had a 50% chance of measuring it there. We have no way of determining which way it's going to go. And one of the interpretations of that phenomenon of that choosing this side or this side is that whenever we measure the particle over here, in a different universe that just sprang into existence, you measured it over here. And so every time an event happens, it happens differently in a different universe that just came into existence. And so you have these kind of diverging universes constantly branching off of each other. And so there are sort of infinite copies of me talking to you, except there's one in which I'm wearing a blue shirt instead of a red shirt, you know, and so on. And that one's really popular because you can get a lot of cool science fiction ideas out of it. But it's a very hard thing to test. And although there are a lot of physicists taking it very seriously as an idea, that there's some sense in which there's sort of this infinite space of new universes all the time. It's very hard to know how to say for sure that that's happening, because once the other universe branches off, we have no way of communicating with it. We have no way of observing it. It's as though it didn't exist to us. And so I don't take an opinion on that. There are a lot of interesting discussions back and forth. Another physicist, Sean Carroll, who is very popular in writing books and talking on social media and such, he takes the position that it's the most natural explanation of quantum mechanics. I don't know how I feel about it, but that's one of the things people talk about when they talk about a multiverse. But there are other things people talk about where in the early universe, there might have been this inflation event that created, you know, sort of expanded our universe. And there might have been other inflation events that created other regions of space that are so far away from us, we can't observe them, but they have different properties of physics in those other spaces. And so that's a kind of multiverse. And even there are even ideas of where you have sort of different versions of string theory in different kind of spaces in this larger space that's not really space in the way we think of it, but a space of theories, and that can be thought of as a kind of multiverse. And those are again the kinds of things that it's quite hard to test, because kind of the fundamental idea of a multiverse is that you have universes that are cut off from you such that you can't communicate with them or observe them. And so you can infer that maybe these things exist, but it's very hard to test whether or not they really do. So I do think that the idea that there's just a larger space than what we observe, and parts of that larger space might have different kinds of physics going on in them, I think that's reasonably a reasonably simple hypothesis. We know that the universe is bigger than our observable universe, which is the region we can see and use light to observe, but we don't know what exactly is out there.
Okay, just one, if you haven't read it, you picked up on science fiction, the book called Dark Matter by Blake Crouch. It really doesn't have much to do with dark matter, I don't think, apart from it's a MacGuffin, and it makes for a nice book title, but it's really much more about the many worlds hypothesis. I would be hard pressed to say I've read a more thrilling book, you know, one of those page turners where you had to get to the end. So it's a service we do to the community on Uplink. So Blake Crouch, Dark Matter, and Blake Crouch Recursion, which I read recently. Unbelievably, well, for me, brilliant books, both of them. So
cool.
Everybody go out and buy. And I am Blake. No, I'm not Blake Crouch. He's a brilliant writer.
The science fiction author Ted Chiang has a book out, a book of stories out recently called Exhalation. And there's a really good many worlds story in that collection as well. All the stories in that collection are very good. But
I read the previous collection. I didn't know we had a new one. I'll go and look that one up.
It's good. Yeah.
Excellent.
Yeah, I just have to it's just not a question but a comment, but yeah, I grew up on Asimov's and science fiction analog as well. So yeah, the short story format is by far my favorite. But on the subject of books and reading, a final question from Rocio. Aside from your own, obviously, The End of Everything coming out on August 4th, we talked about everything. Multiverses, the idea of simultaneous universes existing on top of each other in an infinite pancake. You know, time stopping, going backward. What's going to happen in 100 billion years? So aside from your own, what are the best books? Rocio from Chile wants to know, how do I get into this? What book should I pick up?
So I get this question a lot, and it's a hard question for me to answer because I don't tend to read a lot of books aimed at the general public or aimed at people who are not, you know, active researchers in astrophysics. I read a lot of science fiction, but when I read, you know, popular science things, they aren't usually about space in any way. So it's hard for me to say. There are some books that some of my friends and colleagues have written that I can say they're probably very good. there are very few that I've really read all the way through. So I'm probably just not a great person to ask about that, unfortunately. So yeah, I don't know what to tell
Maybe
you.
we can turn it around somewhere on the stream and get people, you know, people on YouTube or elsewhere on platforms to suggest the ones they've read and the ones from their perspective. Because it's exactly the same thing. I don't tend to read popular science books so often, at least not in my field, because not that I know it all by any means, and it's always nice to see creative ways, but there's so much other science I'm thrilled to learn about, right?
Yeah, and you know, like I have trouble finding time to read, and when I do, I usually want something escapism, you know, with spaceships in it, and you know, and when I read a popular book about a subject that I'm very familiar with, what tends to happen is that I'm reading through it and I'm constantly stopping and kind of trying to back translate to the technical version of whatever they're talking about, because, you know, there'll be some analogy. I'm like, oh, are they really talking about this thing? You know, and so it ends up being quite a lot of work because I know too much. so it's an awkward thing.
Well, I think we can certainly recommend one book, which is The End of Everything, which is out on August 4th. Katie, I got to say, on behalf of everyone at Space Rocks, on behalf of everyone that watched today, thank you so much for joining us. We have a couple of things that we got to ask of you now, though, before you go, before you revert. Mark is a master of this. If you could...
well, we got three things, actually. Three things. First thing is, if anybody has actually spotted this picture behind me, this is because of Nick Cross, who earlier on said, if you're going to talk about the end of the universe, then you have to talk about Milliways, the restaurant at the end of the universe, going back to Douglas Adams' book. So that's what that thing, if anybody hadn't figured that out. The second thing is that at the end of these, we always do the Space Rocks thing, because we can do the Space Rocks thing. So that's space, the Vulcan salute. And Alex is, yes, his thumb's out to the side. He's been practicing.
Yeah, indeed.
And the horns, rocks, space and rocks.
Okay, so wait, is it
space on the right hand and rocks on the left hand?
Vulcan.
Wait, space on the right hand. Space on the right hand?
Yeah,
okay.
Space on the right hand. And
all right.
There you go, great. So space rocks. And then we do that, but we're going to finish with something special this time.
Yeah,
because we know, what do we know, Alex?
We have privileged information online. A few comments have actually come through on the YouTube as well. So Katie, on behalf of everybody who's been watching tonight, happy birthday
to you. Happy birthday to you. Happy birthday, Astro Katie. Happy birthday to you.
Very good. Thank you so much for your time today, and have a wonderful birthday.
Thank you. Thank you. I appreciate it.
Thanks, Katie. Talk to you soon. Bye.
Be well. Bye-bye. Bye-bye.
See you. Bye.